everyone. This is the MRT for various pharmacokinetic models. So this is under Unit 7 what I started in the earlier classes. You already know about the statistical movement theory, right? In that we learned about mean residence time of the drug. How to calculate the mean residence time of the drug through various compartment models is now I am going to explain you. One compartment open model through IV bolus, and then one compartment open model. This is for normally MRT calculation, and this is MRT for multi-compartment model, and this is mean absorption time and mean dissolution time of a drug. So here you need to learn about all these four topics under MRT for various pharmacokinetic models. This is the second topic of your 7th unit. So first let me discuss about one compartment open model through IV bolus. Again your calculations came. Unchanged drug in the plasma or blood. How you are going to calculate the pharmacokinetics of a drug which is following non-compartmental model. So we need to analyze for those types of drugs pharmacokinetic parameters. Either there may be of bioavailability or clearance or of the drug. The unchanged drug in the plasma or blood. This is the statistical movement theory for a drug that follows one compartment open model. So when your drug will follows the statistical movement theory through the one compartment open model, how the calculation will be through your plasma through IV bolus. So first the equation you have to write C is equals x0 divided by Vd into e to the power of minus kt. This is the basic equations. Okay, from this equation we are going to get so many equations. So this is the plasma drug concentration, C is the plasma drug concentration, x0 is the initial amount of the drug available in the body, Vd is the volume of distribution, and this is the exponential form of elimination rate constant, e to the power of minus kt. Okay, and then x is equals to x naught into e to the power of minus kt. We all know about this basic equation. Okay, in the first order drug release kinetics, we learned x is equals to x naught into e to the power of minus kt. So you have to write these two equations simultaneously. Okay, for calculating the pharmacokinetic parameters of a drug which is following statistical movement theory, that is non-compartmental model. So you need to write first these two equations. Then in case of MRT, mean residence time determination, for IV bolus administered dose, all the molecules of the dose start their residence time in the body at the same time. So what is the meaning of this sentence? So it is telling you that once the administered drug particles will enters into the body, they may stay at the same residence time. So here we are stressing out the residence time of a molecule. So what it is saying, the residence time of all the molecules, which are the molecules we entered into our system. Okay, so all the molecules are having the same residence time. Then the rate of change in the amount of the drug, the rate of change, that is dx by dt. So it will be with respect to the time. See, the rate of change is dx by dt. Dx by dt is with respect to the time. Reflects at which the drug molecules leave the body. So here we are talking in the sense of time of the drug molecules, at which time they are going to eliminated out from the body. That is our main aim, right? So what it is saying, that the drug molecules leave the body at any time, that is t. So all the molecules are eliminated from the system. That is the time from 0 to infinity. So you can take 0 time to infinity time to calculate the time of a residence time of a drug molecules in the body. You can consider the time of 0 to infinity time. So you can calculate the rate of change in the amount, that is dx by dt is equals minus k x naught into e to the power of minus kt. You just write down dx by dt is equals minus k x naught e to the power of k into t, small t. Small t is time. So the rate of drug molecules existing at any time t. So we cannot say that all the molecules will eliminated out from the body at a time, single time. So that's why here what it is saying, the drug molecules exiting at any time of t, that will be given by the equation dxe by dt. Dxe is the amount of the drug, that is number of molecules. So we are taking n number of molecules here, n number of drug molecules here. So dxe is the amount of the drug, that is n number of molecules. So dxe by dt is equals minus dx by dt, which is equals k into x0 e to the power of minus kt. So the equation is same, only the difference is here we need to write dxe, that is the amount of drug, that is n number of molecules which are leaving the body at any time t. Therefore, therefore after that, after writing this equation, you can write this equation. The rearrangement of this equation, you will get this. How you will rearranging this equation? You can remove dt here and you can add dt here. Write it down. dxe is equals k into x naught into e to the power of minus kt into dt. Here in this equation, dxe by dt is there. So we are removing dt here and we are adding this. That is, the reaction is undergoing rearrangement. So you will get the equation like this. So then the next step of equation is, you have to multiply this equation with the t, time, on both sides. It will give the residence time of the t. So you have to multiply this equation with the small t, time. So just multiply that. Then you will get dxe into t, that is equals k into x naught into e to the power of kt t into dt. So previously our equation is dxe, just write down this equation, is equals k into x naught into e to the power of minus kt into dt. So we are multiplying with t. So we are multiplying this equation with t, dxe into t, then k x naught e to the power of minus kt small t into dt. So this equation is same. See once. Then the integration of this above equation. So what are the limits we need to take here? Time limits is 0 to infinity, because our drug molecule from initial time to the infinity time. So it will gives you the total residence time of the drug molecules in the body. So you need to divide this equation with the total number of molecules. So we are getting the residence time of molecules from 0 to infinity. It will give total residence time of all the drug molecules. When you divide this equation with the total number of molecules, that means when you are taking the molecules through the one compartment IV bolus dose, it estimates the mean residence time. Then you have to divide this equation along with the integration. See, first you can write this equation, then you need to integrate this equation along with the division of x naught here. X naught is the total number of molecules here. Okay, so integration of from 0 to t dxe into t, right? Dxe into t, which is divided by x naught. Okay, x naught is the total number of the molecules here. Then integration from 0 to infinity k into x naught into e to the power of minus kt t into dt divided by x naught. See, the equation is this. So from this equation, this is the major equation for calculating all the MRT for all the IV bolus, IV infusion, so all the route of drug delivery. So you have to remember this basic equation. Then from this equation, we will get mean residence time for total, that is total residence time for all the drug molecules is, just write down, k into e to the power of minus kt t into dt. So here we are ignoring to write x naught. See, here no x naught is there. Directly you have to write k e to the power of minus kt t into dt. So here you have to remove this x naught. Then you can write it as mean residence time of all the drug molecules. The equation is this. So why we are taking x naught here and why we are removing x naught here? So for the reason is, here we are calculating the total number of molecules, but here we are calculating the residence time of the molecules. So the residence time, it is changing from 0 to infinity time with respect to the exponential form of elimination rate constant. It is not in the sense of total number of molecules. That's why whenever we are going to consider or calculate the mean residence time of all the drug molecules, which are entered into our body, then we can take the consideration into exponential form of elimination rate constant and the time, not taking consideration into the total number of molecules. So here this is the basic equation to derive all the pharmacokinetic parameters for IV infusion, IV bolus. Okay, so that's why here we will take this x naught and here we did not take this x naught value. And then this equation 1, this is called equation 1, right? This equation 1 is divided by the dose. Then equation 1 will develops in terms of amount of the drug in the body. So when you want to divide this equation with the dose, so we are taking all the drug molecules at a particular dose, right? So this equation 1 will develops in terms of amount of the drug in the body. So when we are taking the dose, it will develop how much amount of the drug will be available in our body. So this amount will be total amount of drug available in our body. So that an equation allows to calculate your MRT with plasma drug concentration can be written by substituting C naught into VD for an IV dose X naught. So what does it mean? Instead of writing X naught here, you can substitute it with CO into VD. So just write down, first you have to write this equation 1, then you can write this equation 1. First you have to write that equation 1, that is integration from 0 to infinity. Just write down this dx e t dxet divided by x naught dt is equals 0 to infinity k x naught e to the power of minus kt t into dt. Just write it down very clearly. So this is equation 1, right? Yes, this is equation 1. Here, instead of taking this x naught here, you can take C0 into Vd. This is the initial concentration and this is the volume of distribution. Okay, so in terms of amount of the drug, it will use in terms of concentration of the drug. So here it will be CO only. So you can write down that integration from 0 to t. See, integration from 0 to t dxe into t divided by x naught. This x naught will becomes as it is, and this x naught, instead of writing x naught here, you can take CO into Vd. So this term will be same as that of equation 1. See, once you see equation 1, integration from 0 to infinity dxe into t divided by x naught. This term will be same, and only you have to change this term CO into Vd instead of writing x naught. This whole term will be same. We are calculating MRT here. So then finally we will get the equation of K into C naught into e to the power of minus KT dt by C naught. Here also you can take C naught. Okay, instead of taking x naught, you can take C naught. Okay, x naught is in terms of amount and C naught is in terms of total drug dose concentration. Total drug dose concentration. This is. So that's why here K into C naught into e to the power of minus KT T dt divided by C0 Vd. And then how you can calculate the mean residence time for all the drug molecules? K C naught e to the power of minus KT T dt divided by C0. So then again this C0 Vd you can take C0. So the equations are somewhat conflict. In your textbooks, you did not get anything. So that's why I have written very clearly. You just note it down clearly. Then the equation is, this equation is directly used to calculating the MRT. So if we know that initial concentration of drug molecules, then if we know the time of the drug molecules, then we can calculate MRT directly. And the equation modified by dividing the numerator and denominator by the K. Numerator and denominator by the K. Again you will get one more equation, that is MRT is equals integration from 0 to infinity C naught. Write it down. First you write it down this equation. So this is what the integration from 0 to infinity K C naught e to the power of minus KT T dt divided by C naught, right? So when you multiply this equation with K, so K will get cancelled. That's why this numerator you don't have this K, only C naught e to the power of minus KT T into dt is there. And in the denominator you have C0 by K. See, C0 by K. Okay, up to this mark you just write it down. Then, but C0 into e to the power of minus KT is equals to C0 into e to the power of minus KT. This term will become C. And C0 by K, this is AUC, 0 to infinity. So first you write it down this equation. MRT is equals to integration from 0 to t, then C0 e to the power of minus KT into t into dt divided by C0 by K. This is our equation for calculating MRT. So after dividing this numerator and denominator with K, we will get this equation. Then C0 into e to the power of minus KT term is equals to capital C. C0 into e to the power of minus KT is equals to C. Then this C0 by K, is equals AUC 0 to infinity. So instead of writing these terms, you can replace with these terms. Then the MRT equation is 0 to infinity C into T into dt, which is divided by AUC 0 to infinity. Then this AUC 0 to infinity is equals integration of 0 to infinity C into dt. This AUC 0 to infinity is equals integration of C into dt. So then your equation will becomes integration from 0 to infinity C into T into dt divided by C into dt. Here integration 0 to infinity and here integration from 0 to infinity. This is divided by this. So, why we need to write instead of writing AUC with C into dt? So, what do you mean by AUC? Your AUC will gives you total available area of your drug concentration, right? Here we are taking concentration and here we are taking time. So, this AUC will gives you the information about total available drug concentration at the plasma. So that's why this instead of writing AUC here you can write total plasma drug concentration with respect to the time. That's why AUC 0 to infinity is integration of C into dt. Here integration from 0 to infinity we are taking. So the integration is as usual. So only the difference is C into dt. So if you apply your knowledge in this way, the derivation of this equation is very easy. And then the MRT of a drug after an IV bolus dose. It can be measured from plasma drug concentration versus time data. AUC is from 0 to T is calculating using trapezoidal rule, and the remaining AUC from the last point, that is T star, you can write it like this, T star to infinity. So what it is saying that if you take the total area under the curve, the total available area under the curve, which is remaining the time last point. Suppose you can withdraw the samples first, second, third, fourth, fifth hours. Suppose your timing will be first hour, second hour, third hour, fourth hour and fifth hour. So up to 4 hours, your drug will be released 99%. And then the area available under this 90% of the 99% of the drug will be 98%. This is the area and this is the drug release. So here some amount is remaining, that is some time is also remaining, but you need to conduct the whole study up to 5 hours. So the what is the last point of the time, that is the remaining AUC from last point of the time, that is nothing but T star. This is the T naught initial point and T star is the last point. So for getting this last point, you need to calculate the time from T star to the infinity time. So then how you can calculate this T star to the infinity time? By using integration method, that is by this equation, that is AUC T star to infinity. AUC T star to infinity is equals C star by K. This equation is the most important equation to calculate the pharmacokinetic parameters. So here we are taking AUC. AUC in terms of concentration, because area under the curve will gives you the concentration of the available drug. So here instead of taking T star, here we are calculating the C star. So what is the concentration with respect to the last remaining time interval? That is nothing but your concentration. Concentration is also 10, 20, 30, 40 micrograms, right? So this is the fourth concentration. So this is what the C star concentration, and this is what the T star. This is the last time point, and this is the last concentration point. So from this equation, you can calculate this area under the curve from T star to the infinity. So this equation is equals C star by K, where T star is the last sampling time and C star is the corresponding drug concentration in the plasma. So there is a need. So what we are taking here, ma'am, AUC 0 to infinity we are taking into consideration. So we want to get this AUC 0 to T, there is a need to calculate from 0 to T and T to infinity. So the time, that residence time of the molecules from initial time to the T and from the time to the infinity, we are going to calculate. So that's why your AUC 0 to infinity calculation will involves you AUC 0 to T plus AUC 0 to T to infinity. So T to infinity is nothing but C star by K. That is the last plasma drug concentration, last sampling plasma drug concentration. This term is T to infinity is C star by K. Then if you calculate AUC 0 to T, you can add these two, you will get the area under the curve from 0 to infinity. So this is what the calculation of mean residence time through the IV bolus. So for calculating MRT through one compartment open model, it is not in the sense of either IV bolus or through IV infusion. So generally what we learned under one compartment open model, through IV bolus we learned and through IV infusion we learned. So only there is one difference between these two dosage administrations. In this case of bolus, the drug release will be takes place at a time. In case of this infusion, the drug release is slowly, steadily continued up to prolonged periods of the time. So then, if we want to measure the MRT for the drugs which are following one compartment open model, so what is the equation? MRT can be calculated either by, this equation is nothing but your equation, last equation, that is of this equation. This equation. MRT is, this equation is useful to calculate the drugs which are following one compartment open model, 0 to infinity Ct dt divided by 0 to infinity C into dt. This is used for calculating all the drug molecules which are following one compartment open model. When a drug will be given by a constant rate, so in which cases you are going to give the drug in a constant rate, or IV infusion or by extravascular route, then the drug will spend an additional time. Why? We are giving the drug at a constant rate. So I already told you, in case of infusion, the drug release will take place very slowly. So that's why it needs an additional time. So in the syringe, that means, or at the site of administration, that is in case of gastrointestinal tract or muscle or whatever it is, etc. So you have to remember only one thing: in case of IV infusion or extravascular administration, the drug will require additional time to spend in the body. That is nothing but in the sense of GIT or muscles. Okay. Then you can calculate the mean residence time for selected modes will be using these equations. In case of IV bolus, you can observe the mean residence time of 1 by K. K is nothing but KE. Here K in the sense KE, elimination rate constant. Don't get confused. Whenever they will write capital K, you just remember that capital K suffix capital E, elimination rate constant. So here, in case of IV bolus, I already told you in the third unit, there is no absorption here. Why? Your IV bolus drug will be rapidly entered into systemic circulation. There is no time to get absorption also. Directly it will enter in. There is no need also. Directly it will enter into systemic circulation. So here we have zero absorption. So we have only elimination in IV bolus. That's why here we have Ke. So mean input time is 0. There is no input time. Okay, there is no absorption. See how related it is. And then next, constant rate of infusion. In case of IV infusion in one compartment open model, what we calculated? Have you remembered that? R0. R0 is nothing but infusion rate. So see, instead of R0, here they have written K0. That's it. Nothing is there. K0 is infusion rate. In case of constant infusion, we need to calculate infusion rate. So here absorption is there and then elimination is also there. See. Then mean input time is T half. Then, uh, then this is the observed mean residence time 1 by K plus T by 2. And then extravascular administration, you have an absorption rate constant and elimination rate constant. So the mean input is 1 by Ka. In case of extravascular dose, we have considered the majority, we have considered the absorption rate constant, that is Ka. So 1 by Ka. Here observed mean is 1 by K plus 1 by Ka. So the equations are very simple, the derivations are very simple once you get the concept. This is the MRT for one compartment open model. So then MRT for multi-compartment open model. I already told you that multi-compartment means it is following more than two compartments, greater than two. So how it will be? How it will be. Okay, so it is possible to calculate the MRT for a drug that has a plasma, that is central and peripheral. Here the drug is distributed between the central, you just assume it central compartment, then it is attached to the peripheral compartments, n number of compartments, n number of compartments. Then the assumptions will be made in deriving the MRT of drug that follows multi-compartment. That means the drug is transported between the multiple compartments. So you just assume it as our body as a single compartment in case of one compartment. In case of multi-compartment, our body has multiple compartments for the drug distribution. In that, we have a central compartment, that is, in the central compartment, we had highly perfused tissues, and the less perfused tissues are peripheral compartments. So the drug is distributed from the central to the peripheral. So then there is a need to calculate the mean residence time of the drug for each and every compartment. That means how much time it is spending in case of peripheral compartment 1, in case of peripheral compartment 2. Same like that. This is MRT of the body. That is nothing but MRT of our drug molecules. MRT of our body is MRTC. So C is one compartment, T1 is one compartment, and T2 is one, and Tn, so on. So these all are representing you the peripheral compartment, and this is the central compartment. So if we need to calculate the mean residence time for the drug which is following multi-compartment model, there is a need to combine the mean residence time of drug molecules in the central compartment and in the respected peripheral compartments. Central compartment is highly perfused tissues, okay, kidney, lungs, liver, I already told you. And then peripheral compartments are somewhat less perfused tissues. So there is a need to calculate all the tissues or organs, how much time it is spending, how much time the drug molecules will be spending. So when you add this all the time, you will get the mean residence time of the body. So how much time that particular molecules will have in our body in case of multi-compartment models. So this completes you the mean residence time calculation for various compartment models. Okay, I will continue.